Yes, sir. So, generally, the voltage is directly proportional to, sorry, the impedance is directly proportional to the voltage and also directly proportional to the apparent power thing. So, when the voltage is dropping, when the voltage Vm square, right? So, when the voltage drops, like 1 to zero point 0.9 per unit, then my impedance is getting down by 81%. See how much reduction in the in this. And also, it's suppose if it is zero point 0.8 pu, then 64% means 0.12.84. And similarly, if my impedance is directly proportional to the apparent power, if you are increasing the power consuming is increased, load increases, so power flow will be high. If the power flow is raised by 50%, then the impedance is again dropping to 66%. So this may leads to the operation of your Mo characteristics. So we are having the Mo characteristics like this. So this is the zone 1, zone 2, zone 3. So this is the case. So suppose my JDAP here, maybe due to this load encroachment or power swings, power swing is similar to this. Maybe due to the when you are generating, always the generator should be straight away synchronized with the grid. If any issue in the stability as per the equal area criteria, so that may leads to that, or maybe these load encroachments may leads to this JDAP may falls under this zone. If it falls under this zone, what will happen? It will my zone 2 will pick up. And if the line length is more, suppose, obviously it will be impact on my zone 3. So my relay will be operated without any fault, only on the data, based on the load encroachments. So generally, maybe due to the high power flow or maybe the voltage drop, these scenarios will be applied, will be taken place. So to avoid these scenarios or this, we are having some quadratic characteristics, and also we are having some load encroachment cutting, and also in we can use in the Mo characteristics we can include lenticular characteristics like this lenticular characteristics in the sense here is the zone of protection. Below this, the zone, the protection, the relay should not be protected. Otherwise, by using some blinders, these are the calculations I will share you, team. In this calculation, in this zone only, the protection should be operated or not. But again, how to block this? Maybe this is coming. Actually, the fault is here. When I'm applying this blinder, this with respect to the apparent power, I am blocking this blind with respect to the blinder. But if a fault occur really here, what to do? So I have to block this load encroachment element. So that can be done generally by checking the native sequence overcurrent elements, or maybe during the fault if my voltage is dropped, let's say the low voltage. So that is also one of the indication to bypass these load encroachments. Yes, this is a power swing or load encroachments. So maybe using the quadratic characteristics or lenticular characteristics or using blinders, we can achieve this. And again, to block this load encroachment, we can use if the faults are mostly in unbalanced behavior, like checking the negative sequence to the positive sequence if the greater than the threshold, or going for the negative sequence over current elements, or during the fault, generally, obviously, there would be a drop in the voltage. I am checking the voltage. If it is dropping, saying suppose 0.07 pu, then it is an indication that is a fault, not a based on the load encroachment. That is a kind of a blocking that can be done in the load encroachments and power swings. So this is about the differential distance protection team. So in our this is for today. So in our next class, we will see the protections settings for the differential protection, as well as I will also once again talk about the transfer trap schemes as requested, and ETAP. If time permits, we'll see the ETAP also in next class. Yes, mic is already on. Tomorrow, no class. because I'm having with the other batch. Let's see. Let's say I will confirm you by maybe we will have
This
a class on Friday. Yeah, please.
how you are saying this is a power swing actually that means
Not a power swing, not a power swing. Load encroachment, but power swing also same way of doing, but it depends upon the generator characteristics. So that conditions we have to consider. Same.
Mhm.
See, the philosophy of getting these blinders is depends upon the. See, now this is the general what I derived from the distance protection settings. Now, based on the
Mhm.
load encroachments, or
Mhm.
maybe due to the power swings, this is the concept of load encroachment. Power swing is maybe sudden load change, or maybe
Mhm.
maybe due to the some disturbances. What happens is the
Mhm.
generator will go out of synchronism from the grid. So there will could be a
Mhm.
instability will lies in the grid. So on the so we talk about some concept of equal area criteria conditions that will shows us the whether the generators are in step with our synchronization or not. So maybe those things there would be a chances of power swing will be there, chance of power more or less. That is the other concept. But by considering these both
Mhm.
load encroachment and power swings, we have to ensure that the relay should not be operated under these conditions. That can be achieved by three considerations. One is the quadratic characteristics. Other one is the going with a lenticular characteristics. Otherwise, in the olden, they are using some blinders also. But if I'm again going into this, there again I am misleading with the normal fault currents. These are the general. But I kept this load. This is based on the load encroachment. So again to block this, again I am having to detect the negative sequence overcurrent relays, or otherwise detecting the under voltage. That is one of the indication. The this is the fault that is not based on the power swings or load encroachments.
That means how the relay it will detect this is power swing. How the relay will detect.
I already now let's see now this is the characteristic, right? So now
Mm.
what I done is I am saying now this is the operation. So whenever the ZAP jet measured is be above this, the relay will not operate. If it is falling
Mm.
under this, here zone 3 will operate. If it falls in zone 2, for zone 1. This is the case. Now,
Mm.
maybe this, I am doing some calculation. I will share you that calculation. So,
Mm.
when doing this calculation, I am seeing that this JED application, this JED app is coming to some value, maybe at some 80 ohms or 90 ohms. Let's suppose. Then
Mm.
maybe it falling up to here. So what I will do
Mm.
is I will keep this is the condition that below this relay should not be operated. And again, this direction on the other way of fault, this is the blinder. So in this zone means here only my differential protection always operate. Distance protection, sorry, distance protection always operate in this direction.
Sudden changes in the generator,
Sudden changes in the
voltage
load.
fluctuation.
Yeah.
Okay, load. Okay, there will be a sudden changes in the generator. Automatically, that load it will be changed and voltage also it will differ. So automatically with that voltage and current, automatically that impedance will get changed. When this impedance it will get change actually, it will come under the crop actually. So if it is
Yes.
coming inside the crop, automatically relay it will operate. Correct.
Yes.
But that relay, how that relay will identify this is not real fault and
Yes,
we
sir.
should block
So
it.
now before the relay is operating up to this portion, all portion. Now by adding this load encroachment, I am saying that you should operate only this. This is the zone now for the relay.
Hmm.
Got my point?
Maybe there is some changes actually. See, there is within because there is one setting 5 milliseconds. Suppose the within the 5 milliseconds, this sudden changes if it is happening, the relay will consider see maybe this is it's not real fault. It's due to the voltage changes because the power swinger. If it is slowly, gradually it is coming, then maybe the relay it will detect as a real fault. I think, right? But there is a one setting actually that
That
what
is,
is called
I think that is for the
that in that
disturbance
way only
recorder,
relay
na?
will relay will think this is the real fault or this is the power swing, because power swing also it is coming like impedance change only, and fault also it is impedance change only. Both it is coming under the line under the below the line length actually. But the relay should identify this is the real fault, this is the power swing. Maybe that within the time limit, if it is very fast, if it is happening, that's a real fault. If it is a very, so maybe if it is happening in the very fast, maybe it is fault. If it is happening in the slow, so more than the 5 milliseconds, maybe it will be a power swing, correct? But there is a one setting, that is what I'm asking.
In the power swings and this time setting, I'm not aware. We are giving the, we are making the impedances in the short, that's it. So we are limiting the impedances. And again, for the blocking, we are doing that. For blocking, we are having again, by checking the voltage signals, we are blocking these two relays. That is the one. In the articles wherever, in the IEEE also, the power swings and load encroachments can be attained by these characteristics only, by using the blinders or by using the lenticular characteristics or quadratic characteristics. I think what you said, like 5 seconds, 0.5 seconds, I think that that is a concept of disturbance recorder. Maybe I'm not well about that. Maybe that is the one. But for the power swings, we have to bring this into the zone. And again, maybe there might be a chances this is the fault, but it is showing as a power swing. So the relay will not operate. In this case, I am checking if it a fault, there is a voltage drop. So if the voltage drop is there, then I am again blocking this power swing. I am blocking the power swing and I am opening it. I am giving the relay full space that it has to operate for this zone. Got my point? When first of all, when a fault occurred, I will check whether there is a voltage drop. If the voltage drop is there, I will block this. Then the relay will check which zone, zone 2, zone 3, zone 1, it all operate. If there is a no voltage drop or negative sequence currents is flowing, some characteristics, then I am enabling this one. So then our relay will operate only this portion of the part, only outside of this part. This part, sorry, inside this part. This part.
If it is the fault also, there will be a voltage changes. If it is a power swing also, it will be voltage changes.
Yes, obvious. In the power swings, voltage changes will be there, but there is a no too low of voltage as we can see in the fault, right? See, voltage change will be there, but not too much. Like there is a stability we already maintaining some 0.1 to 10% or 5%. But if you see in the fault, the voltage will collapse like 50% or 70%, 60%. That cannot be. In 220 kV, the voltage won't be, it would be like plus or minus 10% or plus or 5% only. Right? So if I am seeing that fault is much falling beyond this, then I will assume that, oh, this is a fault, not on the based on the load encroachment or power swing. So what I will do, I will disable this feature automatically. So it will see whole the more characteristic and it will detect and it will identify what zone it is coming under.
Okay.
Yes.
Okay. And one more thing, today class finished. I want just know about a little describe about this directional. Can you possibly? I need small explanation from you. Because something it is anything that I will ask you out actually. That is what.
Okay, let me tell you. So generally,
all this covered actually differential distance.
Directional, I already covered.
Because I missed it actually. Sorry, because I have some urgent call actually from office.
Okay, no issues. So let's assume in a simple way I will explain. In our case only we will assume for the distance protection as a backup we will see. We are having 2 feeders and this is the load. And we are having 4 breakers this side. So the now fault, let's assume the fault is in this Y. Here the fault. Though now the fault direction will be this as well as this. Right?
Correct.
Now,
Correct. Yes.
so if the fault is this, all the cities are seeing the fault. But I
Correct,
have to
yes.
ensure that this CTs, this breakers or this one should not be operated for this fault. Means this only this line should be operated. This line should not be operated, because if this line is operated, I can pump the power to the load using this line. That is that is the intention of having two lines for me. Right? So in this case, what I will do is I will enable a directional feature here.
Okay.
I am saying that if a fault in this direction, then this breaker will trip. Similarly, here also, I will enable directional feature. So when a fault occurred in this, then only it will trip. So where you want, generally the directional overcurrent relays will be placed at the load end when it is a parallel feeder. When there is a parallel connecting feeder, and at the load end, you can see the directional overcurrent relays, which will only see this direction. So to see this direction, how can it know? So before in the non-directional overcurrent protections, we can see we are taking only the current signal. But here to do this, we should consider the current as well as the voltage signal also. Both the current and voltage signals to be considered. So now what I am doing is I am considering the voltage signal, and I am and assume that if this is the voltage reference that is applied to the coil of relay coil. This is the voltage I am giving to the relay. So obviously relay is a coil which is having inductance. So the flux will be somewhat lag behind this. Let's assume that is a -5. That is the flux generated by the V reference, pi V. And now let's see if a phases in one phase, I'm having three phases. At one phase, phase to earth, the fault occurred. Okay, if a fault occurred in this phase to earth, then if I am considering the this R phase, Y phase, B phase, R phase voltage and Y phase, if I am comparing the current of I phase and R phase, it is fine. But it is the general now what I am doing. But let's assume if my R phase, if my fault is occurred near to the potential transformer or near to this PTs, or then the voltage will be will collapse. Voltage is very low. So I cannot compare the fault phase current to the fault phase voltage. So obviously we have to compare the fault current with respect to the healthy phases of voltage V, YB. So
that means R phase fault Y and B is the reference voltage.
Reference voltage. So this is the YB. Suppose if I am talking about.
Because the fault phase already there is a fault voltage, it will be dip actually.
Yeah, dip. So we cannot find that. So obviously the current in this case, the current will always be leading to this reference voltage. That's why I am drawing a current way. This is the current. And this is the flux developed by that current, which is having an angle of some theta, which is a fault angle. This is the fault angle. Okay. Now I want to see where I can see the maximum sensitivity of the relay. I mean that how the good relay protection can I see? Means high sensitivity. That obviously can be get by torque. Obviously the torque is proportional to the fluxes of this, both flux of voltage and flux of the current, and angle between them. See sine of theta minus phi. So if I get the maximum torque, then obviously this sine of theta should be equal to 1. Means theta phi 9 should be equal to 90. Yep. So theta equal to 90 plus phi. So the theta is this. 90 plus phi means, so this is the 90 degrees comes to the close to this 90 degrees. It will appear here. This is the maximum torque line. and the angle which is doing by this is the tau. I'm told this is the tau.
Okay.
Okay. Now, now when I'm implement again this here, then the torque is equal to V reference to the I reference and angle of sine of where I'm getting theta equal to 90 plus 5. So theta 90 plus 5 means theta 90 plus 5, it's coming to theta minus 90 plus 5. Right? So when always the torque should be unity, means should be positive to operate. So this should be it is nothing but nothing but cos of theta plus 90, something is there. So this should be minus 90 degrees to plus 90 degrees in this range. So if I'm doing this, it will appear in this zone of this. So that is the zero torque line. So the relay always operated in this zone only. Okay, this is the forward way. Now, forward region. Now again, for the directional, again there would be some leakage current. So I have to give some more again threshold value for this. So suppose if I am giving a threshold value of current is this, then this is the again the restraint position. So the relay will operate only in this zone. This is the forward zone. And if you want to reverse the relay, what we will do, we will take the V reference as a negative, minus V reference, and same. So it is comes under negative one. Yes. This is the general working principle of directional current relay. And also I explained it a little about other relay characteristic angle, everything. So please see that video. If you not,
I'll just go through the video.
Yeah.
But today, apart from this, actually, I started with the different different shapes.
That's it.
Before
That's
that,
it.
what are the
Directional. Yes.
Just I will go through the video. If it is any doubt, then next class I will discuss with you.
Okay, sure.
Yeah, right. Okay, thank you. The next class will be maybe Saturday or
no, Friday.
Okay, right. Okay.
Yeah.
Thank you. Friday means okay after tomorrow.
Yes.
Okay, thank you. Share this video in between. I will go through this.
Yeah.
If I have any doubt, the next class I will discuss it.
Sure.
Okay, thank you very much. Yeah.
Okay.
Bye.
Okay, team. Good night. Thank you.